Well, hello and welcome to another installment of how to make ray diagrams for spherical mirrors. Had a couple already for the concave mirrors, how to do both the ray diagrams to get a picture of where the image would be by bouncing the light rays off of the mirror. And then I also showed the shortcut, which is a mathematical equation technique. It's a little bit cloudy how exactly that math works, and I haven't gone into any proofs of that. It's a bit of messy geometry, a lot of proportions and things like that. So certainly if you're interested, you could look into the derivation of the mirror equation and the lens equation, but that's probably not necessary for you to be comfortable using it. So we're going to now be working on the convex mirrors. This would be the what I might think of as the outside of a sphere when you put an object out there. And if you look at the drawing on the screen, here's our object. We'll continue to use the arrow-shaped object just because they're so easy to draw. And then notice here the mirror comes out in the middle rather than caves in the middle. So that's why we call it a convex mirror. And we're going to look at how the light rays bounce off of this mirror and eventually reach our eye and what our eye perceives as far as the image. And then I'll show you the math as well. So we're on page S30. I'm going to do number 1, and there's a few more exercises after that. It would also be helpful if you had nearby this page here. This is S27. It's got some of the what we call sign conventions. That tells us how we assign positive and negative signs to the values in the math, and also tells us something about the meaning behind those. It's got the rules for how we draw the light rays in the concave and convex mirrors. On this particular problem, we're going to need to use the part that's in parentheses. It says only needed for convex mirrors. So when I read those, you'll notice I include those words as well. And then down at the bottom of this page, there are the equations that we'll do at the end. So the setup is very similar to what we did for the other kind of mirror. We're just going to imagine that there's an object sitting in front of this mirror here, and there's a lot of light coming from somewhere that bounces off of the arrowhead here and goes every which direction. Some of it would actually hit the mirror. In fact, a lot of it would. Now, I couldn't tell you without a lot of geometry work exactly how every ray will reflect off of this mirror, but I can tell you a few because there's some shortcuts related to that, and those are the rules that we have listed on page S27. So we'll apply that. Now, one thing to notice here that's a little unusual is back here is where our focal point is. And it's a rather strange place to have anything on a mirror because it's on the wrong side of the mirror. Remember, if you're looking in a mirror, then usually behind the mirror there's nothing but a wall or a door or something like that. So to have something back here, we have to refer to it as virtual. Anything on the wrong side of a mirror is virtual. So we have here a virtual focal point. So anything we draw back behind the mirror, we have to draw dashed just to remind us that that is a virtual light ray. So in the first rule, it says incident rays parallel to the principal axis, and the principal axis is here, the dashed line, will reflect as though they come through the focal point. So if we start out with a ray parallel to the principal axis, so just draw it right along one of those light gray lines that I included on your page, and draw a little arrowhead showing that this is the one going towards the mirror. It's hard to tell when you're done what's going towards the mirror and what's coming away from it. So those little directional arrows help us. And so if you imagine how something would reflect off of a wall like this if it was thrown straight at it, I hope you can see that the reflection is going to be somewhat up and to the left. So what exactly is that direction? Well, it's up and to the left so that the ray appears to come from this virtual focal point back here. So I always want to draw the real light ray that comes off of the mirror like that. So that's what actually happens. But I also want to draw its virtual extension. So we did this for one of the concave mirror problems, number 3. And we just extend these back because this is what our brain does. When our brain sees a light ray hit, it just assumes that that light ray came from a direction straight back. And so there's the extension for that. Number 2 says incident rays that would go through the focal point will reflect parallel to the principal axis. I'll draw this one in red. Now the focal point is over here, which is why I said it would go through, but it can never reach there. So just imagine a direction heading straight for that from our object. Okay. And then the light ray goes only as far as the mirror does, and then it has to stop because at that point it reflects. Now I'm not going to extend that ray because that is not a reflected ray, that's an incident ray. What I do instead is I see that this one will reflect parallel to the principal axis. So I put my ruler down, parallel with the gray lines, show a reflection back this way. That's the actual light ray that would reach someone's eye. And that is the ray that we have to extend so that we can make sense of what the brain is going to see when that reflected ray hits it. So there's rule number 2. And I'm going to go to rule number 4 because this is the one that actually does not have any parentheses written in it. It's the same for convex and concave. It says incident rays that hit the middle of the mirror, we call that the vertex, it's right here, will reflect symmetrically on the other side. So I'm going to use this little symmetry trick that we've used before. So we'll draw a ray that's going right to the mirror. And then it reflects down and to the left as much below the principal axis as the ray came in above the principal axis. So what I like to do is go back here to where the object is. It's 5 squares tall. So by the time the reflection gets back there, it's going to be 5 squares down. So that's the point that I'm going to head through. 5 squares below my object. And just try to hit it close. So there is what the reflection looks like, using a little symmetry trick. And what that means is this angle up here that I'm pointing to, the angle of incidence, will be equal to the angle of reflection here down below. Okay, this is the only light ray that we can really see the law of reflection applied because we have a dashed line here that is not only the principal axis, it's also a normal line for that particular light ray. So now as before, I'm going to extend that reflected ray back here. Again, you're not going to be perfect on these, but just be close. And then you'll notice right here is where all the eyes looking at this image sees the image coming from. Okay, so that is where the image of the arrowhead is located. I'm going to draw my image in black, and because it's behind the mirror, I'm going to draw it dashed. It's a little hard to draw something so small dashed, but I think if you try, it's easy to miss that too. Sometimes I write down here, that's my image, so that somebody won't not be able to find it. And we can notice a few things then about the image. Remember, we have what in the tutorial Mr. Henderson refers to as the lost method. It's going to tell you something about the location. And so this is closer and behind the mirror. The orientation, notice it's pointing up just like the object was, so we call it upright. The size is smaller. And the T is the type of image. Because it's behind, it's a virtual image. No light rays are actually back there. Now we're going to do the same process using the math shortcut. So I go to my equations, and the nice thing is the equations are the same for a convex mirror as they were for the concave. So if we want to find the image distance, we just need to invert the focal length, invert the object's distance, subtract one from the other in this order, and then invert the whole thing. Now, here's what can mess you up. Only for convex mirrors, you have to assign a negative sign to the focal length. It's because it's a virtual focal point. The math works out only if you put a negative sign on your focal length. So my focal length is how far from the mirror the focal point is. In this case, it's 1, 2, 3, 4, 5, 6. But we have to assign that a -6, and then we invert that. My object's distance, now my object is always going to be in front of the mirror, so that's never going to be a negative. I counted before, it's actually 13 squares away from the middle of the mirror. So I invert 13. Now there is a subtraction sign here. That's not because anything's negative. It's simply because there's subtraction in the equation. And then I invert that. And now we do calculator work. I take -6 and invert it. I subtract the inverse of 13. That gives me -0.24. And then I have to invert that. A lot of people forget this last inversion. That's this one here. And I get a -4.1. I'll stop at 2 sig figs and I'll put it in my units here. And then you always want to stop and do a little check to make sure that this came out consistent with your diagram. So 4.1 centimeters from the mirror. 1, 2, 3, 4. That's real close to where my image ended up on the diagram. And the negative sign is correct because any negative image distance means it should be virtual. And that's exactly what I found before. Then we'll do the height calculation for the image. This is the negative of the object's height times the ratio of DI to DO. The object's height here, we counted before, that was 5 units tall. DI we just found is -4.1, and the original DO was 13. You see that the two negative signs are going to cancel out. And with a little bit of rounding, we're going to get about 1.6. Stop here and look. That's real close to what I get, certainly between 1 and 2 squares tall. Put units on it. Put a box around it because I'm done. And so here again we have a positive number for the height, and that tells us that the image should have come out upright, which it did, and we were pretty consistent with how tall our diagram ended up. So there it is. I think you'll see, with the exception of a little modification of how to draw the light rays, everything else is very similar to what we did for the concave mirror. So once you get used to doing a couple of different problems, it's just a matter of the outcome being a little different. So replay this as necessary. Maybe take a closer look at the final work here. Anything giving you trouble, of course, you can come and see me in the classroom.